With all the preceding concepts and theorems in place, we're ready to answer the important question in this section, which is finding all complex zeros for a given function. In this case, for x cubed plus 8, we know that this is a third-degree polynomial, meaning there should be exactly 3 zeros for us to find. Starting with the signs test, we can look at our given function and see that there are no sign changes, so there should be 0 positive real zeros that we expect to find. And then if we evaluate f of negative x, we would get negative x cubed plus 8, which gives us 1 sign change. So we would expect to see 1 negative real zero in our final solution. We know there should be 3 zeros. None of them will be positive real zeros. 1 will be a negative real zero, which leaves us with 2 complex zeros to find in addition to that 1 real zero. From there, we'll turn to the rational zeros and construct our values for p and q. In this case, our values for p will be based off positive 8, so we'll need plus or minus 8, plus or minus 1, plus or minus 4, and plus or minus 2. And our coefficient in front of x cubed is a 1, giving us only one factor, plus or minus q. In this case, this means our list of values for p is also our list of values for p over q, since we would just take each of those numbers over 1. From there, what we're going to do is take every single value in that list and substitute it into our given function until the result is 0. For instance, if we plug f of negative 2 into our original function, we'll get negative 2 cubed plus 8, which will give us negative 8 plus 8, which is exactly equal to 0. Going back to the factor theorem, this tells us, since we plugged in negative 2 and got a result of 0, that dividing that polynomial by x plus 2 would leave us with a remainder of 0. So x plus 2 is a factor of our function f of x, which means that x equals negative 2 is a 0 for this given polynomial function. From there, what we need to do is take our given function divided by x plus 2, which we now know to be a factor of that function. So setting up that synthetic division problem will give us 1, and then negative 2, and then positive 4, and then 0, which makes sense. We would expect to have a remainder of 0. So the result of that division problem is x squared minus 2x plus 4, which tells us that we can rewrite our function f of x as x plus 2, because we divided that original function by x plus 2, and the result was x squared minus 2x plus 4. So we've moved one step closer to factoring this function. Now what we'll do is focus on this remaining portion, the result of that division step, which we'll refer to as the depressed equation, or d of x. What we want to do at this point is factor x squared minus 2x plus 4, or find its zeros. If this is a function that we can look at and factor, we can apply factoring techniques. Or in this case, since we can't factor that directly, what we'll do is apply the quadratic formula, which will give us 2 plus or minus negative 2 squared. I can write that a little more cleanly. negative 2 squared minus 4 times 1 times 4, all over 2 times 1. Evaluating that and simplifying will give us a result of 1 plus or minus I times the square root of 3. That means we have two new zeros for our function, 1 plus I times the square root of 3 and 1 minus I times the square root of 3. So our zeros in this case are negative 2, 1 plus I times the square root of 3, and 1 minus I times the square root of 3. This is consistent with the fact that we know there should be exactly 3 zeros, 0 positive real zeros, and 1 negative real zero. Since we have a complex number, we also have its conjugate represented, so we can use all of those ideas as checks along the way. And we can write our function in its fully factored form as x plus 2 times x minus 1 plus I times the square root of 3 and x minus 1 minus I times the square root of 3. Where again what we're doing is taking x minus each of the factors or each of the zeros that we found along the way.